you can think of images as maps, right? A matrix of numbers. This matrix of numbers could be like, in general, n by m. So I think here I have present, yeah. Here we think of n by n, then we consider a general case of n by m. So you can have n by n matrix, so it's n by n image, right? N by n pixels. And then you have this x. Now you pass it through this convolution operation. For this convolution operation, you need to know the filter, right? The filter is that guy who is scanning this image, right? And this is almost always a square matrix. So it's always f by f, filter size by filter size. You could have a non-square filter as well, but this is typically not the thing, not the case. Like, you could have it theoretically, it doesn't harm, but you usually don't do it. So we have a f by f filter. This is like, in our example, it was 3 by 3. F was 3, right? And then you start going through the input, right? And then you keep on going over that input by scanning it. And what you get out of it is another map, right? So out of this, you're going to get a map of numbers, another matrix. And that matrix, that output is your feature map, which comes out of the convolution, right? So this is what we show it by z. So x here, if you want to think about mathematical object, x is a matrix, z is a matrix, w is a matrix. They have different dimensions, right? And then you have a stride, and the stride is basically specifying what is the step size that you jump with. We're going to see that we can eventually think always of stride 1, and then whatever we want to do is basically a resampling. We're going to see that. But for now, I mean, you can in general have this stride s, right? And this is what I mean. When I write down this operation like this, it basically means that image gets convolved by the filter, so the filter goes over it, and then you get one map at the output, right? Now, we can write it down mathematically, so just to give you a kind of understanding about this, so let me do it once, and then probably I don't need to do it again. So, if I have this image, if I have this image x, right? So this is my image x, this is x, and I want to do the convolution. So my filter is f by f. Where do I put first my filter? I'm going to put it on top left, right? So I'm going to put my filter right here. So this is my filter going here. So this is f by f. And then I have this filter. This filter has different weights, right? I multiply them with the entries of the corresponding entries of the matrix. I sum them up. I write this down on the other side, right? So this is going to be my matrix Z, right? And then this guy, after getting multiplied, is going to come over and sit here, right? Everybody's cool, right? So this is what's going to happen if I want to compute Z 1, 1, right? Entry 1 on row 1, column 1. Then I basically get my matrix, multiply it by x1, 1, right? And what is x1, 1? That is basically x from 1 to f, 1 to f, right? This is the column index. This is the row index, right? So what is happening inside x? X starts from 1 to f here, right? And again, 1 to f, right? And then I do the multiplication. This is going to be z1, 1, right? Everybody's cool? So what about z1, 2? If I want to compute z1, 2. So still row 1, the second column. What should I do? I'm going to, right now, assume I'm doing it with a stride 1. If I do it with a stride 1, what do I do? Push 1 right? So the thing that is going to happen is that this guy is going to start from here and ends here, right? Correct? So where is the start point? 2. And what is the end point? F plus 1, right? Now if I just keep on going, if I am thinking, so in this case, my x or my filter is going to get multiplied with x1 to f on row, but on column is 2 to f plus 1, right? Now, if I think in general about one guy here on this first row, this guy, and that is z1j. Where should I start this filter? So when j was 1, I started from 1, right? When j was 2, I started from 2, right? If I go on a general j, it's going to be j, right? So I can write it down j here, right? But I can also write it down this form, 1 plus j minus 1. You agree, right? That's the same thing, right? Everybody's cool, right? Now, where do I end? I'm going to end again at f, right? When I start at 1, I'm going to end at f, right? When I start at, when I go for 2, then I'm going to end up at f plus 1, right? So if I go for general j, I'm going to end up at f plus j minus 1, right? Now, the thing that I did was when I have a stride 1, if I have a general stride s, what's going to happen? First time I start from 1. Second time I'm going to start from s, right? And third time I'm going to start from not 2s necessarily. Each time you add up s to it, right? So it's going to be like, just think about s equal by 2, right? So your matrix is going to start 1 to f, right? The next one is going to be 3 to f plus 2, right? Correct? Next time is going to be 5 to f plus 4, right? This is going to be the case. Now, what is happening here? J minus 1 times s, right? You start from j minus 1 plus j minus 1 times s, ends up at f plus j minus 1 times s, right? So this is when you are doing with the stride s on the first row, right? Now, you finish with this first row. What do? You're going to jump exactly the same way on the rows, right? So this means that the next time you're going to start from 1 plus s, f, and you go till f plus s, right? The next time you are going to go for 1 plus 2s, f plus 2s, and so on, right? So this is in general the part of matrix that you're scanning, right? And your weight is always getting multiplied with this part of matrix. This is always an f times f part of your matrix. You add up everything, and then you write it down for z, right? So you don't really need to memorize anything here, because anytime you want to do it, you see it, what is happening, right? That's just to give you the formulation. So this part of x is essentially the part that you're looking into. You multiply the weight into, and then you add it up, putting it there, right? Everybody's cool? So this is going to be the convolution operation. Exactly the same thing that we did in the example, right? I'm going to do some numerical examples for you so you get comfortable with that. Questions? Okay, so that guy is convolution. And now that you are finished with convolution, so if you remember in our example, what did we do? We got this perceptron. We built the filter, right? And then we started to just scan the whole image, right? And then in our example, what we saw that we don't really need to activate before saving the numbers inside the output map. We could just save the row numbers inside that output map, right? And then as long as we have at least one number which is positive, right, then we can say that we have detected X pattern inside our image, right? Right? So that was the kind of feature map coming out of the neural network, or that convolution, if we just do it without activation. And if we want to just say whether there is x or not, what do? We basically get this guy. We take out the maximum one. We see whether that is positive or not. We just activate that one. If that one is 1, this means that there was at least one x here. If it was 0, it means that all the features we computed were negative. It simply meant that there was no subpart of the image looking like x, right? No pattern x. Everybody's cool, right? So what we are doing here, we are computing a bunch of numbers, right? And then after doing that, we are just pulling out some features out of it, right? Some conclusion out of it. And this is basically the idea of doing the pulling. But the pulling is not only that. I mean, it does more, and you're going to get feeling about that. But this is some sort of, pseudo-activation process to the feature you computed. Now, what you do in practice, you do not get your whole feature map and do one pulling out of it. Usually what you do it in form of filters again. So this means that you take a look at this part of the image, you take the maximum number out of it, right? And then you save it here. So that maximum number here is definitely the positive one, right? Because the positive feature is inside this window, right? Then you keep on going exactly like what you do in the convolution. With some specific stride, say stride is 1, so you're going to jump one right? And then you look at this one, you see what is the maximum number, you're going to save it here. And again, the plus number is here within the window, so definitely the maximum number that you save here is the plus 1, right? Everybody's clear? So what about the next pulling? If I do the next pulling, would it be positive? No, because if I go one right, then it's going to be definitely negative, right? And I keep on going like this. When I am over, I get to the new row, right? And in this row, the maximum is again positive, right? Everybody's clear? Everybody's cool? So I keep on going again. Next one is again positive. Then it's negative, right? And from now on, anything that I collect is going to be negative, right? Because if I go for the next line, it's going to be negative as well, right? Now, you just get all of them out of it, and this is going to be your map, right? Right? Now, this map still has the information about your original image, right? Because there are a bunch of positive numbers there. So this guy, this new map, is still telling you that there is x inside your image, right? But this guy has one difference to this one. If you look at this guy, everybody's negative, right? There is one pixel inside the map which is positive, right? So there is a very spiky behavior inside the map, right? But looking at this one, is it as spiky as this one? No, right? So this guy is less spiky because it has a bunch of numbers which are positive, right? Even the negative numbers are larger because each time that you wanted to collect the negative number, you took the maximum one, right? So this is the whole idea of pulling. The pulling, what it's doing is actually filtering out, smoothing out your feature map. And why we are doing it, you're going to see it gradually throughout the course, throughout this chapter. That you see, doing this is going to make your decision making more reliable because you are not just deciding based on one particular feature coming out of a local computation, right? So this is somehow smoothing out everything, right? And this is a kind of very useful behavior which makes the convolution operation works better. So this is the idea of pulling. Don't worry, we're going to define it concretely later, but this is what you basically do. And once you have this one, still if you give this one to your classifier, like you say, look at the whole thing and tell me whether I have pattern inside my image or not, then your classifier is still able to detect the pattern, right? Because there is positive numbers there, right? So that would be the pulling. Yes, you got a question?
So the magnitude of these four numbers are different, right? Just the first
Right, definitely. Here, the maximum is different. This is the maximum is +1 because we know everybody else is negative. Here is the same. But if you had a larger number here, then this would change, right? Definitely. Yeah. But the key point here is that if you look at one particular number here and you compare it to the guy here, that one is now depending on everybody here, right? This is going like this number that you get is the maximum of all of these guys, right? And this could, you're going to see a numerical example. That one would change less frequently. But you can simply do it by your own. Just write a sequence of numbers which are varying a lot, right? And then put a window on that. And for each window, you just write down the maximum number. Then you see that one is just fluctuating less.
I mean, by intuitive, I think the perfect match will have the highest value.
Sorry?
I mean, if it's a perfect match, it will have a higher value.
I mean, in this example, yes, but not in general, right? So we're going to see that later. I mean, this idea, I mean, these numbers here are for a simple binary classification, but in general, you could have like a, it might be not even a classification problem, right? And then those numbers that you get here, all of them have meaning. So it's not only a binary meaning whether the pattern is here or not. And then that filtering would help. Yeah. But we're going to see examples, so no worries. I just want to give you the intuition before we start. Yes?
I wonder if the stride is the same in the full layer and the core and the previous layer. Because we have strides here and there, right? Is it the same number?
Sorry, I didn't get your question.
Because we have stride
Yes, yes.
in the convolutional layer and also in the pooling layer, right?
Yes, yes.
Is it the same number?
Oh, yeah, yeah. We typically what we do. I mean, you're going to see it later. You do the convolution with the stride 1, and then you just put the stride for pooling layer. But as you're going to see shortly, stride is not important. It's just a sampling. So we can simply forget about it. At some point, you don't care about the stride anymore. Yeah. But typically in practice, a stride is just given to the pooling. Like pooling is going to reduce the size, typically. Yeah. Questions? No question? Okay, so yeah, that was this regarding the pooling, and you can of course do the pooling with higher stride. Yes.
Just a higher level question about convolution versus fully connected. Is this just for images, and is the only difference?
No, you can have any. I mean, if you put your data in a form of a map, you can use convolution all the time. And actually, it comes from the fact that you do know that you have a sort of shift invariance inside your data. You're going to see it later on when we just interpret the convolution CNNs as a sort of, a form of MLP with less weights, less connections. But no, there's no reason for that. I mean, one of the most primary kind of data that have that property are visual data, of course. But you could have a sort of data which is not visual, but you still do know that it has this property. It means that the information is somehow locally collected in parts of that data, right? And it could be like data you collect, like confusion maps you get out of analysis of data, right? They are also very good kind of data. You can give it to the CNN.
The neural network behind it, apart than using the filters and the strategies, is the same thing?
Yeah, it's always the same thing. You don't care. I mean, even for data that is not like that, if you do know that the data is not too complicated, you can use the same thing, and it's going to work better than MLP. The MLP of the same size. I mean, this guy, whatever that is going to work better than the simple perceptron. Yeah, definitely. Yeah. So, questions? No question? Okay, so if you got no question, then this would be basically the main idea of building a convolutional neural network. So what is the idea? You have one convolutional layer always. That convolutional layer is basically doing the convolution, scanning that we talked about. Then you compute some map out of that convolution. And when you get that map, then after that, you're going to do pooling, right? Why we do pooling? We want to filter out. Sometimes we want to reduce the size. And then you get another map And now that you have this map, maybe you want to keep doing that, right? You do another convolution on this guy, do pulling, convolution, pulling, till you feel like, okay, this data has been processed enough, right? And now you have this final one. What you're going to do, you're going to just flatten this one. And we're going to talk about that. No worries. Flattening simply means that you just get your map and put it in form of a vector, right? So you start from the first entry, first pixel here, you put it first, second, and so on. And now you have a vector. This vector, you can give it to a MLP, right? One fully connected neural network, right? Now, what is happening here that you started with a giant data, maybe a very high resolution image, right? And then you were able to somehow, with a significantly lower number of parameters, process it into a very small map, right? And that small map, hopefully, is collecting the crucial features of that giant data, right? And that smaller map now is able to be processed by MLP. Whereas if you wanted to just give the whole data into the MLP at the first point, you needed a giant MLP, right? And that giant MLP might simply get lost because it has so many ways that it cannot really focus on the features, right? So you eventually start with the image, for instance, but you gradually process it into a tiny form of data sample. That tiny data sample has actually very good separation of the features in its own entries, right? Maybe the original image is image of a cat with a ball inside the site, and then there was, nice weather with a tree and so on and so forth. And then this final map is a bunch of numbers. This guy, which is coming out of the very last layer of pulling and convolution, is a bunch of numbers. Some of them are telling you that, well, there is an animal there, and that animal has these properties, right? Some part of it says that there is a ball in it, and that there is, or maybe there is something that people play with, and its color is roughly red, right? The other one says there are some green stuff inside the image. Now, you have these features. These go inside the MLP. The MLP can classify properly, right? So this is the main thing that you do with convolutional neural networks. So as I told you before, they also have a fully connected part. This is what we already have done. But in order to be able to process data properly, we first just do it by convolution. Okay? Everybody's clear? And of course, you can imagine that we do it with significantly higher number of layers, right? So you're going to get significantly deeper, right? One example is, for instance, VGG16. We are going to talk about it once we are over with the parts of CNN. So once we understood that, then you're going to understand details of every operation in this network. You're going to understand what these numbers are. I mean, you easily can follow this, right? But this guy is significantly deep. I mean, to the current standard, it's not that deep, but at its own time, it was very deep. So you see that you get a convolution layer first, then you do again convolution, so on, till you get here, right? And at this point, this is the point where you say, okay, the convolution processing is enough, and then I have this kind of data, so I'm going to sort them out into form of a vector, and then I just give it to MLP, and that MLP is going to classify the image that was given to the whole network, okay? So as I said, we are going to talk about it later, but I just wanted to give you a very motivating sort of introduction to the idea, okay? Everybody's clear? Questions? I mean, I look like a bit of angry or sad person today, but it's not really. It's just my neck is hurting a bit. So you feel free to ask questions. So it's just, I cannot really, scan a lot. So, yeah. So, yeah. Okay. So, yeah. Now, as I told you initially, this was the same idea as the people in this, this Hubble and Wiesel study found out about the, a natural visual cortex of animals. So what they concluded was something of this form, and basically you can now see what we are somehow doing in convolutional neural networks is basically mimicking that process. So what they said that you have this input layer, and by input layer, it simply means the visual scene that is directly going inside your visual system, right? And then the live creature is looking that those reflections go directly inside the visual system. Then they somehow modeled it in this form that there is one layer of S cells. It's simple cells. Okay, they called it simple cells. And what it's doing is like every single cell is looking into one part of that visual scene, right? And somehow is getting some signals out of it. Now, again, like what people early days did with perceptron, they modeled that sort of signaling by this linear operation that is somehow looking at that image, is computing some sort of, mathematical signals out of it, and they sum it up, right? So every single simple cell is basically doing one of the elements inside your feature map, right? It's just doing that convolution for that part, right? And they felt like, okay, all of these guys are basically working with the same kind of logic. So it's basically they have same filter, right? So when you look at this scene, one cell with the same logic is looking into this part, another one is looking into this part, and so on. But how you start to recognize that, oh, that guy is there, right? So they said, like, these simple cells are collecting some signals, but there are some C cells behind them, which is complex cell. And those complex cells are actually looking into this part, for example, a subpart of those simple cells, right? And then looking at that, they look around them and see what are the signals they get, and whether these signals, any of them, is indicating whether what you're looking for is there or not, right? This is basically that idea of pulling out, right? And this was the reason that people somehow built that computational model. Now, the thing that is happening here is that inside the C cell, when you are looking into your simple cells, right, you're looking in a part of that, right? And that part could be small. But given that every simple cell is also looking at a part of the original image, this means that those complex cells behind the simple cells are somehow looking into a more broad part of the visual scene, right? This is what we call a receptive field, and we have it also in the convolutional neural networks. We're going to talk about it again. So what it means that it's true that you might not imagine, well, when I'm looking at this scene, I am not, how can I just see everything there and then suddenly I start to concentrate on one point? The point is that there are some cells behind the scene that they are able to somehow get the signal from a bigger part of the image, right? And that one is telling you, oh, you should focus here, right? And then gradually they are going to narrow it down. Since your brain is somehow focused on this part, then you narrow it down, down, down until you get to the target, right? So this was the idea. Well, I'm not in the position to say whether this is, like, it's a very old study, and I'm not in the position to say whether this is a really realistic model or not, but at least this is something that is working with the artificial systems, right? And it might be very simple modeling of what is happening inside our cortex, but that at least helped us to this point, right? Okay.